My name is Peter McKinnon. I've taken over from Jack Smith, the gentleman who helped start this initiative, due to his poor health and subsequent passing just less than a year ago. We're having a special event in May that will be celebrating Jack's contribution to foresight. Because he's a well-known pioneer. In fact, one of the speakers will be somewhere either in Singapore or Manila, who has been a student of Jack's and practices foresight in East Asia. And so uh, this initiative, as I say, is an eclectic group of people. It's not student based per se, although it's sponsored by the business school, and it's basically a continuing education, if you like, at the adult level. But it's not credited in any way. It's just people with a serious interest in the future and the various topics that we raise. And today, our topic is courtesy of Jeff Krehmer. And Jeff, as some of you know, is a professional engineer, mechanical engineer, graduated from the University of Calgary in the I guess it was early 90s, 1992. And he has been working as the head of his own company that is uh, something what
Mechanical engineering
yeah,
consulting, yeah.
yes, big time. There we are. I couldn't find it. I couldn't remember. Yeah, big time engineering corp. A nice, a big aggressive name. And he's got a topic today that's kind of on a big scale too. You might have noticed, some of you might have noticed that there's a difference in the initial post for this event had a different title, and we conjured that maybe this would be a more appropriate one. And so it's obvious what this means: Arctic infrastructure opportunity. And Jeff is going to talk to us about some of his views about the energy opportunity and the transformations for helping develop our Northern Territory. Jeff
Yeah,
also spends time working with Boy Scouts and has written a book that you can no doubt see in his background over his right shoulder, and he may speak to that to the in some of this, and of course it's illustrated on the uh, first slide here that's called Infinite Resources. So, Jeff, I'll pass it over to you. The format of the meeting was Jeff will give us about a 50-minute presentation. If there's any burning questions or comments, if you would raise your hand or actually put it in the chat would be the best. But otherwise, not to interrupt until it's time for a Q&A. And that will be followed, a formal Q&A will be and discussion. It's not just a questions and answers discussion. And then we will cut the discussion from the point of view recording, and we will able to be off the record. So with that, I gather we're recording now. Is that correct, Samir? Are you still with us? Samir is our webmaster.
it was recording when I came
Yeah,
on. So.
I did have to press it. Okay, so over to you, Jeff. It's the floor is yours.
All right, thank you. So first, I'll just say that the company name Big Time Engineering Corp is aspirational. Right now, it's a single man operation. And when you registered, you might have noticed that the title originally was Canada's AI Judo Move. And the idea behind that was that it is taking it something that is considered a disadvantage, which would be the cold in the Arctic, and using that to our advantage. So this is still the same presentation. I've changed it from ice to intelligence, and the reason should become obvious as we go through this. So just a little bit of housekeeping here. So to make it easy to follow where we are in the presentation, I've got this little color code here. So right now we're at point 1 in the lower left-hand corner. And as we go through the presentation, we'll follow the color of the rainbow. So the next part will be context, data center requirements, global energy in the Arctic, a new clean renewable energy source, bonus benefits, and observations and conclusions. So let's get into it. I expect this talk is going to be about 50 minutes long of me presenting, and then as mentioned, we'll have time for questions. And I'm willing to stay as long as there are questions. So what do you see in this image? Oops. Let's do that again. So this is artificial intelligence generated image. Of course, we see the frozen sea ice, the frozen landmass without any vegetation, the northern lights and stars up in space, and a weak sun on the horizon here. So a lot of us would consider that to be a frozen wasteland and inhospitable to life. And of course, there's snow, darkness, and for indigenous peoples of the Arctic, that is considered home. That is their home. So what you don't see here are plants and animals living under the ice, liquid water below the ice as well, the temperature of the air, and the temperature of space. Now, it's interesting to note that the Arctic Ocean and the Southern Ocean are the two most productive oceans in terms of biomass per cubic meter. So obviously it's AI generated image, and that'll come to play next or later on. So 16% of the world's oil and 30% of the world's natural gas is believed to be in the Arctic region, and there are other resources. So Canada essentially has all of the elements necessary for modern society. Currently, a lot of them, like the rare earth elements, are not being mined, but we do have some active mines in the Arctic. We got high purity iron ore from the St. Mary's mine on Baffin Island. And right now, that ore gets shipped off to Europe for production. And I think Sweden and Germany are two of the largest countries that purchase the iron ore. One of the things I'll be talking about briefly is how with excess electricity, we can produce hydrogen, and then we could potentially upgrade that iron ore into green steel and use hydrogen to reduce the iron oxide. And then we'd still have a little bit of coke for the carbon content of steel, but it's possible. But my main point here is that there's a lot of resources in the Arctic that currently aren't being tapped. They're known to be there. And as we explore and develop the Arctic more, I'm sure that more resources will become available as well. So some stuff that's been in the news recently. So Prime Minister Carney recently announced that we're going to be purchasing over the horizon radar from Australia and building that out. So northern sovereignty is a big issue. Artificial intelligence and sovereign compute is also a big issue, particularly with the United States becoming more hostile to Canada. And Canada is also developing satellites for, again, sovereign communication. And this announcement was just made on March 13th. We announced yesterday over $40 billion of investment in the Arctic. And that was done at a press conference in Norway with the Chancellor of Germany and the leader of Norway as well. So established here, we have Canada investing in communications in the Arctic, military defense for terrestrial sovereignty, sovereign compute, and economic resource development. Let's talk for a moment about the value of artificial intelligence in the context of the United States. So these are the top 7 companies on the New York Stock Exchange listings. So NVIDIA, Apple, Alphabet, Microsoft Corporation, Amazon, Meta Platforms, and Broadcom. So this market capitalization, that just means if you took all the stocks of those companies and sold them at current market value, this is what they'd be worth. So NVIDIA, they started out making video cards for computers, but they ended up being really good for doing computations in general. So they're used with artificial intelligence and they're used with cryptocurrency mining. They are worth $4.5 trillion. So these are all AI related companies, these top 7. There are 2,223 New York Stock Exchange listed companies with a total market cap of $44.7 trillion. And those top 7 are worth 46% of the entire New York Stock Exchange. And that does not include privately held AI companies like OpenAI or xAI. So gross domestic product of a country is a value of money that's produced within a certain period, usually a year. And this is the top 10 economies around the world. So the United States, China, and Germany lead the pack, and Canada basically gets in there under the wire at 10. So if we compare their GDPs to the market cap of NVIDIA, well, since this graphic was made, uh, um, these countries, these gray countries, are the only ones that had a market capitalization that was greater than, or a GDP that was greater than NVIDIA's market capitalization. And since this graphic was made, these three have fallen off the list. So it's now just China, the US, and Germany that have a market capitalization that's greater than NVIDIA. And Germany is very close to falling off the list too. And you can see the numbers vary a little bit between these two charts, but the point is it's close. So former CEO of Google, Eric Schmidt, has a few things to say. He predicts, or has testified to Congress, that 99% of all electricity will be used to power super intelligent AI. So if you think of all the power that's being produced at the Hoover Dam and the Grand Coulee Dam and all the nuclear power sites and gas turbines and wind turbines and et cetera, he figures that will eventually be 1% of the electricity use, and 99% is going to go to AI. And he says the United States should become friendlier with Canada or Saudi Arabia to get access to enough generating capacity to power AI data centers. So I like this quote. AI is a learning machine. When the learning machine learns faster, everything accelerates, and it accelerates to its natural limit. The natural limit is electricity. He also expects that the United States will need an additional 29 gigawatts of power just for AI to stay competitive with China by 2027, and that number will go up to 67 gigawatts by 2030. And then a personal observation here, Saudi Arabia is hot, but Canada is cool, and that will become apparent. The reason I mentioned that will become apparent shortly. So the Trump administration last year called the AI tech leaders and flew them out to Saudi Arabia. So it's pretty clear who they want to ally with. All right, so let's talk about other tech leaders, what they have to say. OpenAI's new data centers will draw more power than the entirety of New York City, 10 gigawatts. We're building, this is Elon Musk, we're building gigawatt-sized facility outside of Memphis, Tennessee. Satya Nadella of Microsoft. Energy supply has become the defining challenge in AI infrastructure. The biggest issue we are now having is not compute glut, but power. And then Mark Zuckerberg of Meta, we would probably build out bigger clusters than we currently can if we could get the energy to do it. Energy constraints have become the largest bottleneck to building out AI data centers. So what do AI data centers need? They need compute, they need connectivity, they need cooling, and they need power. So the compute is relatively easy. There are commercially available data centers that you can buy in a shipping container. You plug it in. This is a 1 megawatt facility, and it says 1 megawatt of IT heat rejection. So essentially, everything that you put into a computer chip ends up as heat. And computer chips are pretty delicate. They have a certain temperature range that they like. If you go outside it, they start getting computational errors and can destroy the chips. So what's the advantage of shipping containers? Well, they're scalable, portable, they have rapid deployment, they're relatively energy efficient, there's cost savings, and so on. As far as connectivity in the Canadian Arctic, there is currently a data pipeline being built between Japan and the UK. And I know that this section along the coast of Alaska has already been completed because all of these communities are now connected. I also know that by 2030, the Canadian government has announced that Iqaluit here on Baffin Island will be connected as well. And you can see that they're also planning a connection to Quebec along that line. This section here, coming from Alberta and British Columbia up into the Yukon and Northwest Territories, this is already completed, and it extends to the Arctic Ocean up to Tuktoyaktuk. So Elon Musk, of course, beyond being a car manufacturer and robot manufacturer, also contains the largest network of satellite communications. That's another option for communicating to the internet for computers. At this conference, the Abundance 2026 conference, he made this comment. The economy is going to 10x in 10 years and we'll have a base on the moon. Now, he did put in the caveat if we don't have World War III. So take that for what it is. Musk is already planning on building solar-powered orbiting data centers. So he wants to take advantage of the solar energy. But I would say that putting a data center in space, I think that's a brilliant move. It's going to make it a little bit hard to service if something goes wrong. Okay, so computer network power requirements. This is just the US grid from 2008 to 2020. It had an approximate growth of about 8% per year. And if we can grow it using green energy, that's the best. Of course, any type of energy that we can get is going to be necessary for fossil fuels or for AI and data centers. This is a graph, and this is an old graph from 2019 here. They were expecting, this is the power requirements of Bitcoin, just one of the cryptocurrencies. And they say by 2019, they were expecting, or sorry, that was the power that Spain puts out by 2019. But you can see that at this point, back in 2022 approximately, Bitcoin was using about as much energy as Finland and almost as much as the Netherlands. And I've read that they're expecting it to be about as much as all of Italy in a few years. Italy, of course, is a G7 country, so that's a significant amount of energy. Now, this is an interesting graph. This is fraction of US data center electricity used in 2014 by end use. So 43% goes to powering the servers. This is what I equate with the compute capability of the data center. 3% of the electricity is used for network, 11% for storage, and a whopping 43% for cooling. So you can see as much energy goes into cooling the data centers as actually operating them. So cooling equals power. This is a graph from McKinsey and Company predicting where the energy expansion is going to go in the United States. You can see, or North America, you can see that the bulk of it's going to go to operating data centers. In Europe, that's going to be the second highest use of new electrical production. And in China, that will be the third highest use. China and the developing world are still focused on using electricity for industry, and in Africa, that's also for electrifying homes. So traditional barriers for AI, a reliable continuous source of energy. So dams, hydroelectric dams, nuclear power, gas plants, coal plants, if you're still using coal, those are all viable sources for powering AI data centers. You also, in most jurisdictions, if you are building a large electric grid, you need to connect to the grid, which requires these high voltage transformers for stepping up and stepping down the power. The lead time is a minimum of 2 to 3 years for that, partly because of the increased demand, partly because of things like war in Ukraine, where Russia attacks the electricity infrastructure. And we're seeing something similar going on in Iran and soon to be Cuba by the looks of things. Then we also need sufficient water for cooling, not just for the power centers, but for the data centers as well. And wherever you build these things, you're going to have opposition. So it was recently announced that there's going to be a large 1 gigawatt data center built in central Alberta, not far from where I live. And there's already people in opposition to it. And even though they fast track the electrical connection to the grid, which in Alberta can take 6 to 8 years if you don't fast track it, they still are facing that opposition. So you can imagine if you live in Olds, you might not want a gigawatt of natural gas to be produced in your backyard. It just might affect your property value. And then the other thing is red tape, bureaucracy, and getting permits and so on from the government. So in a place like Olds, you got the municipal, county, provincial, state, and federal governments. And then you also have indigenous interests, environmental groups, and so on. So there's lots of different forms of red tape that prevent these projects from moving forward. So energy is all around us. Of course, solar energy is ubiquitous and represents nuclear fusion, electromagnetic radiation. And we got hydropower, which of course has potential energy caused by the gravity of the Earth and the varying pressures of the waterhead. And then chemical energies and solar. So we're all familiar with these. Energy is a form of difference of potential. So in your car, when you burn fuel, you increase the temperature of the air in the cylinder, you extract some work from that, and then you release that expended air out into the atmosphere through the exhaust pipe. So this is an image of the energy that is being used in the world currently. We've got traditional biomass, so that's your wood and animal dung for things like heating and cooking your meals. Then the next 3/4 of the graph are coal, oil, and natural gas at approximately equal representations of the power that they provide. And then after that, we've got nuclear, wind power, wind and solar, and then biofuels and others. So that gives us a problem. Climate change is related to burning fossil fuels. There's also pollution. Millions of people die every year because of air pollution. And the competition to what I'm proposing is just business as usual. And all of the energy that was consumed in 2022 amounted to 178 trillion, well, 178,889 terawatt hours. So of that, just looking at the cost for the fossil fuel side of things, natural gas, oil, and coal combined came out to about $3.7 trillion, and that's annual. That's the annual average between 1999 and 2018. I expect with what's going on in Iran these days and the spike in oil prices, it might be a little bit higher this year. So Canada's GDP, for comparison, is about 2.2 billion per year in US dollars. All right, let's go back to high school for a moment, high school chemistry. You may recall if you take a chunk of ice and you heat it up, it'll heat up, heat up, heat up, and it gets to 0 degrees Celsius, and then it stays at 0 degrees Celsius as it melts. And then after the ice is completely melted, the water temperature rises from there. Now, that works in reverse as well. So when you're melting the ice, you have to add 334 kilojoules per kilogram. When you're creating the ice from liquid water, you get 334 kilojoules per kilogram. So 1 kilogram is 1 liter of water. So that's 334 kilojoules per kilogram. So if you look at a cubic meter of water, that's 1,000 kilograms, and that represents 334 megajoules per cubic meter. So let's take a look at what happens every year in the Arctic. If you look at this, there's a dark blue line that represents the average sea ice extent between 1991 and 2020. You can see that the ice freezes, the sea freezes from James Bay through Hudson Bay all the way across the Arctic to Russia, and then from the Bering Strait to the Franz Strait. The maximum extent of the sea ice is 15.1 million square kilometers. And then you have the minimum extent, which happens in September. Again, the dark blue represents the average, and the lighter area represents the situation for that particular year. Excuse me. On the far right, you can see the difference in the types of ice. The dark blue represents single-year ice, and the other colors represent multi-year ice. It's expected that within the next 20 years, there won't be any more multi-year ice. It'll all just be single-year ice. Anyway, the difference in sea ice extent between maximum and minimum is 10,730,000 square kilometers. So I won't bore you with all of the technical details, but that represents, just in the energy of freezing and thawing the ice, represents about 5.6 times all of the energy that humanity uses in a year. So the question is, imagine if we can use that to replace fossil fuels, and I believe that we can. So Canada's northern territories compared to central Alberta. This is Canada's north. So up here at the northern tip of Ellesmere Island, there's a military base called Alert. And then there's a few scattered communities across the Arctic. Why am I showing you this? Well, we'll get into that in just a moment. The population of all of Canada's territories, so this Yukon Territory, Northwest Territories, and Nunavut, if you add up the populations, you get 130,620 people. For comparison, I live in this community of Black Falls in central Alberta. The next community north of me is Lacombe, and the community south of me is Red Deer, which is about halfway between Calgary and Edmonton. The population of those three centers is 132,000. The area is approximately 10 kilometers east to west and 50 kilometers north to south, so 500 square kilometers compared to the Arctic, which is 3.8 million square kilometers. A significant difference. So Canada's Arctic represents 40% of our landmass and less than 1% of our people. And why is this important? Well, Canada's greatest defense is about to become its softest underbelly. The north of Canada, that open border, more importantly, and then there was a break in the conversation, more importantly, China, Russia, and the great powers and the United States fighting it out over the Arctic with the vast resources of the Arctic is going to be the great game of the 21st century. That's Steve Bannon, who is an advisor to President Trump. He has suggested that the United States should seize Canada's Arctic. Let's take a look at that place I mentioned, Alert, up in Nunavut at the end tip of Ellesmere Island. You can see that for 5 months of the year, there's essentially no sunlight at all. That's what this black represents here. And then for 5 months of the year, you have almost continuous sunlight. And in between, you've got the shoulder seasons. The mean daily temperature is around minus 30 degrees Celsius for half the year, and it gets up to a balmy almost 4 degrees Celsius during the summer. All right, so what's the innovation that I'm talking about? Ocean atmosphere temperature differential energy conversion, what I call OTEC. If you're familiar with OTEC, ocean thermal energy conversion, very similar concept. By the way, this isn't my idea. It was written about decades ago, but it hasn't been popularized. So this is the general idea. If you have air at some temperature, let's say minus 27 degrees, you're going to, well, let's open this up. So again, that's the energy cycle. I got a few more clicks here that I'll get to afterwards. But I want to say, here's the low temperature, the atmosphere at minus 27 degrees. And then we've got the hot temperature at minus 2 degrees. And in this case, that takes into account what we call pinch in engineering. That means that we can operate a large heat exchanger on a temperature difference of plus 3 degrees Celsius in the deep ocean. The water, even in the Arctic Ocean, is warmer if you go down deep. In the tropics, of course, it's the opposite. It's warm at the surface, but it gets down to a temperature of about 3 to 4 degrees when you go down about a kilometer or so. And we can use that temperature then to produce energy. By the way, minus 2 degrees Celsius is the temperature that seawater freezes at, so we can take advantage of that the energy given off as the latent heat of fusion when seawater freezes. So we have liquid and a working fluid, which in this example I'll say is propane. Liquid propane gets pumped below the sea ice where it gets warmed up. The work for the pump is only 11.6 kilojoules for 1 megawatt of output that I'll talk about in a moment. It goes in and absorbs about 12 megawatts of heat energy from the ocean, and then the heat engine is able to produce energy at about 7% efficiency, which in engineering terms is not great, but it's free energy. And that gives us 1 megawatt of net power output, and then we reject 11.9 megawatts of heat to the atmosphere. So you see that this all fits out. The 1 megawatt that we're extracting is electricity, plus the heat output that's going back to the atmosphere equals the same as the energy put in absorbing the energy from the ocean. What's interesting about this is you can scale it to whatever size you want. So you build a larger power plant, larger heat exchangers, everything scales up. You can make whatever amount of energy you want from this. Also, I'll talk about this in a bit more detail in a moment. Removing heat from liquid seawater produces potable ice and cold brine. Now, if you live in the UK, as a few of the people here do, you have a huge benefit in terms of the Gulf Stream and the Atlantic meridional overturning circulation. Scientists tell us that it's at its lowest point in terms of strength in about 3,000 years. But basically what happens is you get warm water coming from the tropics that releases a whole bunch of heat into the atmosphere, which is why in London you don't generally have snowstorms, whereas Calgary, which is at the same latitude, experiences very cold winters. That heat given off is estimated to be the equivalent of a million gigawatt power plants, just continuously natural cycle heat exchange from the tropics to the Arctic. So what we're doing here is we're basically mimicking it. We create ice to produce electricity, and the result is that cold brine falls to the ocean floor. That essentially strengthens the Atlantic meridional overturning circulation. For 1 megawatt, we can expect to produce about 38 kilograms per second of ice. Let's look at that if we add an extra twist to this system. So again, the same power input, the same temperature, the same mass of ice being produced, but we're going to this time add 1 megawatt of heat energy from cooling a data center. That increases our temperature of the hot end to 35 degrees Celsius. That increases our efficiency to about 20% for the heat engine and gives us an additional 0.154 megawatts of output. And then, of course, we got heat being rejected to the atmosphere. So again, if you scale this up to 1 gigawatt, the power production would generate about 39 cubic meters of fresh water per second. How about in the summer? Well, you've got 24 hours of solar energy. Maybe we can do something with that. This is just one idea. You could use traditional photovoltaics as well. Okay, so what have we got here? A scalable technology. So we have a bunch of data centers. A bank of 16 data centers would represent 16 megawatts of power. Of course, we can double that to get 32, 64, 512 megawatts, and then a 1 gigawatt stack would look something like this. If that looks at all familiar to you, it might be because of these sorts of things. Everything here is scalable, modular, easy to reproduce. And of course, the shipping containers and the stuff can be all built wherever it's cheapest to do so, and then shipped to your power plants floating in the Arctic Ocean. So if we look at, again, the power requirements of data centers, we got that 43% as we discussed. So this is what I would call, the Palo Alto compute equivalence. So we'll say that for a 1 megawatt system, we get 43 Palo Alto compute equivalents per megawatt. If we build that same system in the Arctic, just scaling up the storage, drive, and network costs, and then the energy from the servers rather, we can scale that up to get 76 PACE, or Palo Alto equivalents. That's a 74.4% improvement in compute using the same amount of electricity. But wait, there's more. Because we can generate more power from the waste heat of the data centers, the overall power efficiency increases. So essentially, we can get double the energy output of what you would be spending to operate the same thing in California. Plus, the electricity is more expensive in California. Plus, the taxes are more expensive in California, et cetera, et cetera. So each electron used in a polar energy platform produces twice as much compute as an equivalent energy used in Palo Alto. Let's talk about economic activity from artificial intelligence and data warehousing. So this is just the market capitalization of all the cryptocurrencies. This is a bit old. I don't know what it is these days. I prepared this slide about a year ago. I should update it. But at that time, the market capitalization of all cryptocurrencies was about $2.7 trillion. And of course, they need compute to operate all these different currencies, and they're willing to pay for that electricity. Artificial intelligence, the AI market. Now, this is kind of funny because we're here in 2026. They estimated about 900 billion. You already saw the market cap was significantly higher than that. But let's just take these predictions in terms of the geographic expansion of the industry. You can see that it's going to be significantly higher in the near future. So, and then cloud computing, you've got data warehousing, which is already a $3.4 billion market back, or they're estimating by 2032. All right, so can this be profitable? You can go online and choose your own calculator. This is from bestcalculators.com. And I just manipulated the numbers. So I said 556 servers with an average power per server of 2,000 watts with 90% utilization, power efficiency of 1. That works out to 1 gigawatt or megawatt rather. And so you can see what the expected cost of electricity to operate that would be. So it's about $72,000 per month. Well, that expense for the data center is revenue for the power plant. So if you take that 72,000, multiply it by 1,000 megawatts for a gigawatt plant, and you multiply that by 12 months per year, you end up with $864 billion per year. Now, if we assume that you have to pay for the material and stuff, we'll just say that there's $400 million of profit out of there. At the Nunavut corporate tax rate, that works out to $48 million per year, and Canada's corporate income tax at 15% works out to $60 million per year. You can literally have thousands of these things operating in the Arctic, and if you listen to Eric Schmidt, that's exactly what the future is going to hold. So that's a lot of potential revenue for those governments. Disclaimer, this is a thought experiment, not investment advice. So other bonuses. Well, this isn't a bonus, this is a fact. About a quarter of the world's population doesn't have access to reliable drinking water or water for general health, like taking showers and so forth. And currently there are 2 groups that I'm aware of that are doing experiments to thicken the ice because, of course, one of the concerns with global warming is that melting sea ice is going to greatly affect the climate. So if we can thicken the ice, there's a benefit to that. So I'm not sure. I invited Fonger from Arctic Reflections to attend today. But anyway, this group is working in Canada's Arctic right now. They're based out of the Netherlands. Real Ice is based out of the UK, as I understand it. Note what they're doing here. They're pumping seawater onto the ice. So the normal way this happens is the ice forms naturally. And as you can see in this next slide, when seawater freezes, however, the ice contains very little salt because only the water part freezes. It can be melted down and used as drinking water. So what those companies are experimenting with is great in terms of keeping the water cool, but it also introduces salt above the ice, which means that it's not entirely in harmony with the natural system of things. Whereas what would be happening in a power plant is you'd be producing the ice below the water and then shipping it out on top of the water. So what can we do with all that ice? Over 30 cubic meters per second is a significant amount of ice. In fact, a 1 gigawatt plant running at high efficiency would still produce about 5 million cubic meters of water in 2 weeks. So these are the dimensions of cubic ice. Of course, water when it freezes expands, so it's 1.1 times its original size. And this represents a typical tractor trailer load, and this would be 1,000 tractor trailer loads. So here's 400,000 tons of ice, and then you would put those together, and you can ship these around the world. So I like to say, imagine this almost kilometer long chunk of essentially ice in shipping container, or not shipping containers, but in these tankers. moving through the Strait of Gibraltar, and you're sending water north and south to all of the countries along the Mediterranean. Most of those places would appreciate getting additional water for their system. But one thing that I like to point out is that in 2023, the global bottled water sales were approximately $342 billion worldwide. That's just water. That's not pop. That's not beer. That's just water. And so what else can we do with that? Bonus number 2 is we can use that electricity to produce hydrogen. This is what I was talking about with the green steel earlier. Hydrogen, of course, is a precursor for other chemicals, but it can be used directly as a fuel. It can also be used to lift aircraft, and currently Canadian Pacific Kansas City Railway is using hydrogen in their locomotives, in one test locomotive that I'm aware of. Last I heard, it was operating between Golden and Revelstoke. But you can also take that electricity and convert the hydrogen with some nitrogen from the atmosphere to produce ammonia. Ammonia is a much easier chemical to work with in terms of transportation and liquefaction. The other thing is it's a precursor for things like fertilizers and explosives, both of which will be needed in industrial quantities if we're going to be doing mining in the Arctic and, of course, farming. And the other thing about ammonia is it can be used directly as a fuel. So modifying existing diesel engines so that they can run on ammonia is a relatively straightforward thing to do. Market shares in 2024, they were looking at about $204 billion of hydrogen, which is expected to grow to $603 billion by 2034. And likewise, ammonia is about $213 billion and just expected to grow by about 5% CAGR. So bonus number 3, if we have electricity and a well-insulated container and we get the water from the ocean, we get the heat from the ocean, all we need is some fertilizer and some seeds, we can pretty much grow whatever we want in a controlled environment. So we can generate produce for northern communities and the military. Right now, if you want to buy a salad in Iqaluit, you're probably going to pay about 6 times what it costs for that same salad in any of the cities in the south of Canada. Then the other thing we can do is open ocean fish farming. As I mentioned earlier, the polar oceans are the most bioactive oceans in the world. The most expensive thing in this fishing operation, this is a deep sea fishing operation, the most expensive thing is the platform. Well, if we already have a platform to generate electricity, that should be not a big deal to expand it a little bit. The food chain in the Arctic would be completely natural. All we have to do is shine some light into the ice, which is essentially what happens in the summertime. The sun comes up, the algae under the ice grows in mats and absorbs all that solar energy, converts it into good things like omega-3 and omega-6 fatty acids. And then the other critters, come along and eat the algae. Those would be copepods and such, and then the fish come along and eat the copepods, and we get the benefit of having omega-6 fatty acids in our salmon. Now, note that that is different than fish farming, where they're using things like wheat to feed the fish, and that's not as natural a process. And also in that case, then those fish farm salmon are not getting the omega-3s, whereas doing this in the Arctic Ocean means that they would actually be getting the nutrients they would normally get. So sushi restaurants, grocery stores would be the market there, and that is a $277.3 billion market as of 2025, expected to grow to $370 billion by 2029. Very quick growth in that industry. The other thing to point out is this is already larger than all the sale of cattle, like beef, in the world. So looking at those barriers for AI that we discussed earlier, well, on a polar energy platform, we have abundant, clean, renewable, reliable, continuous energy source. For a 1 gigawatt grid connection, there's no need to connect to the grid because you're going to be using the energy on site. So you don't have to worry about transformers and all of the time to get them. And then polar energies are literally floating in the ocean. So even though we wouldn't be using the water for waste heat dissipation, we're going to use the atmosphere. It's available and it's non-issue. There are many locations in the Arctic that are more than 100 kilometers away from any human habitation, so I don't expect NIMBYism should be a problem. And there's also fewer levels of government and red tape to deal with, especially if we can get this kind of industry to be declared in the national interest or of national importance. So the United Nations has 17 Sustainable Development Goals. I think it should be pretty obvious from the presentation so far that SDG 6, clean water, we can help with that. Affordable clean energy, we can help with that. Industrial innovation and infrastructure, yep. And responsible consumption and production, absolutely. And climate action. In my book, I make the case that pretty much all of these things can be advanced by building polar energy platforms. And it's a little bit dicey when you get to things like gender equality, but I try to make that case too. Also note that it's the decade of ocean science and sustainable development. So let's look at Canadian government expenditures. Now, I want to point out this again was made more than a year ago, so these numbers are old, but this is what the Canadian government was paying for Arctic support. And if we add that up, that's about $5.7 billion per year on a total defense budget of $26.5 billion and the deficit of $40 billion, with $496.9 billion of total expenditures in 2023. Again, comparing that to the market capitalization of NVIDIA, that looks tiny. So NVIDIA last year had $215.9 billion of revenue. There is money to be made in artificial intelligence. So polar energy platform benefits and approximate global markets. So this is just a summary of what we just looked at. So there's local electricity, clean electricity, and hydrogen. Jobs, tax revenue, domestic goods, international trade, research, infrastructure, military support. The compute that we talked about, data houses, $37.4 billion. I don't know if powering global data centers is a $100 billion industry at this point, but it will be in the near future, certainly. And having sovereign compute, well, that's just priceless. Aquaculture, we said, is already $277 billion. Potable water, just for bottled water, $342 billion. Humanitarian aid, human health, greening the deserts, those are all priceless things. Energy, so we saw $3.6 or $3.7 trillion in fossil fuels. We could potentially replace that market with enough polar energy platforms. Now, of course, we might be talking 100 years, but it's possible. I make the case in the book that it could be done within the space of about 30 years if we did it as a global project. All right, so the total Canadian federal territory support was $5.7 billion pre-2026, and total federal government expenditures $496 billion. So how do you get involved? We would like to make the Arctic the AI powerhouse of the world. We need partners from Indigenous communities, government, especially government, to reduce red tape, to assist with loan guarantees and other funding opportunities. And we need business people of all types. So how do you get involved? Well, first, let's just talk a little bit about some quotes in the industry. So this was rewiring the energy system is a multi-trillion-dollar business opportunity that's good for the climate, good for humanity, and good for sustainable economic growth. That's Dr. Sultan Al-Jaber of UAE on November 15th, 2021. One of my favorite people in the whole world, even though I've never met him, is Peter Diamandis. He says the world's biggest problems are the world's biggest business opportunities. He also says the best way to become a billionaire is to help a billion people. And I love this quote because it touches on so much of what I do. Imagine a world of 9 billion people with clean water, nutritious food, affordable housing, personalized education, top tier medical care, and non polluting, ubiquitous energy. Building this better world is humanity's grandest challenge. So, looking at this picture, what do you see here now? For myself, I see an opportunity to improve the lives of billions of people around the world. So, there's my contact information. Please contact me if you'd like to get involved somehow or another. This is the link to my book's website, infiniteresourcesbook.com, or you can go directly to Amazon and get the book from there. So we know how to do this. None of the technologies that I've described are beyond modern capability. In fact, organic Rankine cycles, the ORC cycle, has been known since we were building steam engines. And let's make it happen. So I'm ready to take questions at this point. I see Prabir has already got his hand up.
Thank you very much, Jeff. That's a very interesting and aspirational presentation. I am sure that there'll be a number of questions and comments. As the chair for this event, I guess I'll take the first question and pose the first question to give people a chance to think up their next remarks. And in no particular order, I was just thinking if you're looking at like the life and harvesting from the ocean in the future. There's the deal cycle, and I'm just wondering how that might be affected in if you're thinking of commercial fishing, for example, in the Arctic Ocean, because the deal cycle is that 24-hour up and down over hundreds of meters in the global oceans where life basically certain life descends as the day gets lighter and others rise as the day gets lighter, and these vary over every 24 hours. And if you got seasons of darkness and seasons of continuous light, it completely disrupts the deal cycle. And so that
So
would have an impact on commercial fishing, I would think.
the deal cycle operates in places that have a day-night cycle. So the Gulf of Cortez, the squids go down
Yeah,
into the depths and then they come up and
yeah.
feed at night. That I don't know if that cycle operates in the Arctic or
Yes, it does.
Antarctica.
Yes, it does.
So even if it does, I don't see what the issue is because in the summer you naturally have 24 hours of sunlight, so that's great. And so the algae, the algae isn't moving; it's just living underneath the ice. And
Right.
so
Yeah.
if there's a cycle, I don't know what drives the cycle. Like, do the copepods go into the depths? They can't go into the depths during the light time because it's light for 6 months.
Yes, it's at the extreme. Yes.
Yeah. So
I'm just, I'm just questioning. I mean, it's just a Gedanken experiment here. I'm just questioning in the sense of could there be an impact on because of the deal cycle on commercial fishing? Because it's very sensitive in a polar region because of the
I,
day night cycle.
yeah, as far as like when I'm talking about fish farming and stuff like that, um, uh, that's being done in fjords in Norway. It's being done, as we saw in that image, in deep ocean platforms, and that's actually the benefit now. When you do the fish farming and have a high population of fish in a small area, they actually make the local environment toxic. But if you can go in the deep ocean, then those wastes can drop to the ocean floor, and they're not an issue for the fish that you're raising, basically. So one of the things when I mentioned that last year at the Arctic Energy and Resource Symposium in Calgary, one of the first questions somebody had is like, "Oh, you can't do that. Have you done any studies?" And my answer was, "No, haven't done any studies. I would love to do a study. Let's do one. Can we set it up? So let's find out if we can farm fish this way and if it affects the local environment negatively or not. I personally, on the surface, it doesn't look like there should be any negative effects. Since it's all natural process, we're not adding mercury to the system. We're not adding pesticides to the system, which your farm fish might have because they're being fed on grains and stuff like that. So this would be completely natural, eating copepods and stuff like that feed on algae. I think it's a good win-win. Okay.
Hey, Robin Davis, I see that you put a comment that you might wish to ask directly to Jeff. And I'm looking to see if there's others who would put anything in the comment for questioning or discussion.
Well, let's take Prabir after Robin because he's got his hand
Okay.
up, I see.
Oh, yeah,
Yeah.
Prabir. Sorry. Yeah, we'll take
I,
Prabir
I, I,
after Robin.
I do have questions, but the comments that I put in the chat was just about the data centers that XAI, etc., are building at the moment, that they are known to be toxic, use toxic chemicals, chuck out a load of toxins as well, and are being investigated. But I'll
Maybe
Perhaps.
put the question in the chat and I'll talk to Robin's point while you do that, okay? So Robin, in terms of toxins and stuff, the system that I'm describing, everything would be in shipping containers. It would be self-contained. So I'm not sure, like the construction toxins and stuff like that would be local.
No, I wasn't talking about your solution. I'm saying that what they're currently doing to actually manage the power problem is that certainly the US government are giving these companies like XAI permission to actually build their own um, power generators to actually
Absolutely.
power the new data centers because the grid can't take it. But
Yeah.
all those current power stations are toxic. So
Yeah.
your solution will be a lot cleaner.
I expect so. And in Quebec, just they're using hydropower for running cryptocurrency companies and stuff like that. So this isn't the only clean solution. If you have wind power and solar energy that's connected to battery systems, that's perfectly acceptable as well in terms of being non-polluting. And one of the nice things, if you go to fission using, say, a clean, safe fission technology like thorium or as a nuclear reactor, one of the other benefits of that is you get the primary power generation, but then you can use that waste heat to enhance this vapor cycle that I was talking about. So, all right. Did that answer what you were trying to say or speak to it?
Yeah, I mean, I was just putting a comment in there about the state of it at the moment. I mean, it is going to be a race between these AI companies that have got permission to build whatever power stations they actually need, which are very bad for the environment and everything else, versus the cleaner solutions that are around there. They just need investment. But by that stage, you know, however long it takes, will we, you know, will we already have polluted our world even more with their interim solutions?
Yeah.
Will they care?
So, I mean, I can envision a system where essentially we are running very clean and without with hardly any pollution at all. Um, of course, there are going to be pollutants that are used in the creation of the steel, or there's going to be pollution that's created in construction, and the various components are going to involve pollution. So it's not like it's 100% clean, but the operation side of it should be. So, Prabir, did you manage to get your question in there? So, has the
Yes.
concept of polar energy platforms been raised before the Arctic Council as a possible collaborative project? This is why I'm doing this presentation. I'm looking for people to work with who have the connections to go ahead and do that. So, I have no idea about even how to get involved with the Arctic Council. So, if there's somebody here who's doing that, great. Well, Prabir, let's talk offline. I would absolutely love to work with you to reach out to the Arctic Council. I did do a presentation last year at a symposium in Calgary. That was the Arctic Energy and Resource Symposium. They're about to have another meeting again in a couple of weeks. But anyway, the concept, it's been a long road for me to get this out in front of people. And I'm hoping that with the Foresight Synergy Network, the connections to government and such, that we'll be able to get the word out and find the resources necessary to do a pilot project. I mean, I'm talking about billions of dollars here. We can do a pilot project where we, might set up a testing station on a lake in Northwest Territories, for instance, Great Bear Lake or something, or Great Slave Lake, and just prove the concept out. Have 2 shipping containers. We might be able to do that for like $5 million or something.
So while Prabir is doing that, I might mention Jeff, and to those who are new to this group, that I noticed some of the names here, just to give you some context. I noticed meteorologists and economists and computer science types. So I'm wondering if, for example, Derek Ireland, you might have some comment, both from an economic, social economics point of view, as well as the AI point of view, because you've been doing a lot of work in that area yourself, just to put you on the spot. And Bill Pugsley, perhaps I believe you're a meteorologist. Is there some useful question or comment you might have in regard to what Jeff has presented? So if just to go on the record, if you guys would like to do that. But Preber, are you ready to try talking?
Let's try once more.
Excellent.
Yeah, it works.
Oh, it worked.
Yep.
First, Jeff, a clarification. It's 20 years ago since I was with Industry Canada that I worked with the Arctic Council group. So your first task is to find somebody, presumably within Industry Canada or Northern Development, who represents the government of Canada and the Arctic Council. One of the things that became very clear, and there were 8 members, circumpolar countries in the Arctic Council at that time, before the falling out with the Russians. One thing that became very clear is that the Russians started their northern development 100 years ago with their northern route. And they have cities in north of the Arctic Circle which have populations several times greater than our 3 northern provinces. That's by way of background. My point is that surely it's more economic to generate powers through PEPs in the Arctic than to put 1 million satellites in space. Why does this argument not come through?
Well,
I mean, of Elon Musk.
I don't think Elon Musk's heard about this project yet. So,
well, that's something different. But if the guy's thinking of putting 1 million, by the way, it's never been clear to me who gave him the authority to put the 1 million satellites. That's a different question, because I thought that the ITU might have something to say about that. But it seems to me that this is an obvious alternative to look at.
Yeah. So, like I mentioned, it seems to me logical that you would be able to service something that's here on Earth much more easily than you would in space. And the idea of putting satellites in space, it wasn't original to Elon Musk. Other companies are talking about it too. The advantage, of course, up there is that you've got a free source of energy in the sun.
Yeah.
And with the satellite network that he already owns with Starlink, it's easy to get that data from basically, it doesn't even have to be in close Earth orbit. It could be far away from the Earth, relatively speaking, beyond geostationary, let's say.
Jeff, if you're a science fiction fan of Asimov's, as I was, 75 years ago, this idea of having satellites in space which would capture solar power and beam it to Earth was explored in science fiction. I'm not saying the idea is new. All I'm saying is if Elon is willing to invest in 1 million satellites, surely you would have expected the guy to look at terrestrial alternatives.
Well, I mean, we're all products of our experiences, right? So he just like, he's a science fiction fan too, and he just might not have read the same books that I've read. So the book that inspired all of this is called Engineer's Dreams, and it's just one part of a small chapter. This was written in 1953, I think, by Willie Ley, and he talks about OTEC. So the idea of using the temperature difference between the ocean water, the surface ocean water, and deep ocean water. And there are companies that are doing that work as well. I have some contacts who are involved with that through LinkedIn. But the trouble with that is there you're looking at a temperature difference of only
small.
Yeah, it's like maybe well, you're looking at 4 degrees to say 28 degrees, so 24 degrees, and then you lose efficiencies on both sides, so you end up having like a 10-degree difference, and that's not enough to make it commercially viable, because in that case you have to pump the cold water up from the deep ocean, and there's losses with that. In what I'm proposing, you can actually take advantage of the cold brine. You use a chimney effect, and that can draw the fresh water in for you. So you don't need to do any pumping at all.
Uh, Jeff, maybe you could drop your last slide and we could have images of the group.
Oh, okay.
You'll find in Zoom there's another tab at the top of your app, which will have meeting. So if you click on that, you get to see everyone's faces instead of
Can
the
you guys
slide.
see it now? Or do I have to actually exit out? Hang on.
If
And
you
at this point, I'll just step in and thank the speaker, and then we can turn off the recording so that we can talk freely if you so wish to do so. Jeff, thank you very much for a very informative and far-reaching, I'll call it, I guess, a proposal. It certainly dovetails with the federal government's ideas of
Yeah.
national projects on a grand scale, and there's certainly going to be a much bigger focus on the Canadian North in years going forward. I have a background. I spent about a decade on polar expeditions, so I know a lot about the tough life and living and working in those kinds of environments. And so, with that, I'd like to thank you again, Jeff, for your thoughtful presentation. And you might give a pitch on your book in terms of how to get access to it. And we'll now have continuing discussion, and I'll turn off the recording. And Chris, if you're still with us, you made a statement about wondering why or how they are building these data centers in deserts. So maybe you could pose your wondering statement, okay? And we could have some discussion. I'll turn off the recording. Thanks, Jeff.
Yeah, thank you. And yeah, again, to the book is the website is infiniteresourcesbook.com. And you can also go directly to Amazon if you put in my name, Jeff Krehmer, with Krehmer. You will be able to find me on Amazon. I'm the only person that I'm aware of with that last name who's an author there. So, yeah, so it shouldn't be too hard to find.